We'll also draw, okay? So while I draw for sodium, you can draw, and just the outermost for the iron will do. We'll draw these as half arrows. So that's the tradition that we follow, and we'll see what these half arrows mean. They correspond to the spin of the electron. Okay, so we talked about the principal quantum number, azimuthal quantum number. Then there comes a magnetic quantum number. Okay, the magnetic quantum number will tell you about the orientation of the orbitals. Now, we'll look into that when time comes. But for now, let's just fill these orbitals, because these. Anyone has any problems with like this, with this box representation? Because this is just 1s, 2s. This is 1s, 2s. This is 2p. 2p type A, B, and C. So we can say X, Y, and Z, something like that. And then again 3s. So if you're getting in the electrons, you are filling up. Yeah, so there's another thing, that the spin. So you want to, so if one person has, so in India, it's a very crowded country, okay? So sometimes in the train, so we have a lot of trains. So you do not always get like a confirmed booking on a train berth. It's like a country of 130 billion people. No, that's wrong. 130 crores, so it's 1.3 billion people. So it's a small space, but it's a heavily dense population, okay? So sometimes it might be really like awkward for you, but sometimes in a train journey which is overnight, we don't have that lot of like flights. On a berth, it's like a seat in which you can sleep, but sometimes two people get assigned because it's so crowded. So if I'm like traveling with my brother, what we do is I sleep from, my head is this side and my leg is that side, and he has the opposite. It makes it easier for us to adjust. So imagine similar thing is happening in here. So let's assume there's one electron coming in like this. The other electron is coming just the opposite. So it's opposite spin. That's what we call it in technical terms. Okay? So there are two electrons coming in, two electrons getting filled here. For 2p6, we know that there are 6 electrons that are going to be filled here. How do you think an apartment like this, which has 3 rooms, is going to fill? Say you have 6 people, so 6 people have lined up. So the first person comes in, you assign it to a room. Where do you think the second person would want to go? Would you go to the same room? I would not. I mean, I imagine you don't know each other. Like it's just you would go to a second room just in case. Like you go to this room. The third person comes in, goes to this room. Now the fourth person comes in. Now there's no choice. It's like, so I use the concept of like Olympic city, like in my example on YouTube. So the fourth here, fifth here, and the sixth here. Okay, and now there is this one person coming in here. Okay, so this is just a way of representing. Okay. Now tell me, if you have Na plus, where will that electron come out from? From here, the outermost. This is the electron. So for Na plus, the electronic configuration then becomes 1s2, 2s2, and 2p6. There is the 3s gets knocked out. Okay, so this basically becomes 2,8. Now, Courtney, you were telling about the 8. Sometimes this will not hold true, but most of the cases it will. Okay, we'll discuss like why not. But yes, you would want to have like this is like the octet rule. This has been seen to be true for many cases. And so the thing is, nature works in a certain way. We are trying to understand how nature works and come up with some kind of solution, some kind of a hypothesis first to understand how these things work. because you do not know everything that is happening in the universe, sometimes your ideas are half cooked, sometimes heavily flawed. Okay? And that is why there might come something that does not fit into your rule book. That does not mean nature is not following its own rule. It's us who are not able to find out what that rule is. For now, let's assume nature follows this octet rule. Okay? Let's assume nature follows that, okay, if I have 8 electrons, for some reason, I am stable. Okay? If that serves the purpose, it serves the purpose. For that reason, can you, so this was the 2-8-1. So Bohr-Bury's principle is like the octet rule. And the other thing is, for these orbitals, there is also a stability. So why is octet favored? It is more stable. For some reason, it is becoming more stable. Okay? Just converting the Bohr-Bury's into Aufbaus from KLMN to SPDF, and you convert it, there is this thing that you have to keep in mind, that full-filled orbitals are more stable than half-filled orbitals is more stable than partially filled orbitals. What this means is, if you have, so what a full-filled p orbital will look like is something like this. A half-filled will look something like this. And a partially filled can look something like this or this. Same for D. So we have a D, the full filled. So all of these different small 5 rooms having 2 people each is like full filled, more stable. And the next is a half filled. Also, this is also an example of partially filled. This is also partially filled. Same for D's. Okay. If we think that this is true, then we can also explain a lot of things in chemistry, if we assume. And this kind of goes to that 8, and they talk to each other in their weird way, but not always. But that's why SPDF is important. Now, based on this, let's try iron. What's this noise? Okay, let's finish this. Can you tell me why Na plus was stable? So why do you have Na plus? But will you have Na plus? Is it stable? Can I have Na2 plus? I'll write Na2 plus. Nothing can stop me. 2p5. I'll have Na2 plus. I'll have Na5 plus. But why nature does not have an Na2 plus? Generally. I don't know, there might be some weird things happening in some part of the universe. I don't know.
It's not going to want to get rid of an electron in the 2p.
Why?
It's already stable.
Right, because if you go from Na plus to Na2 plus, you'll have to go 2p5, and it will look something like this. So this is 2p5. Right? This is a partially filled orbital, which is very, very unstable, or less stable than a full-filled orbital. And that is why Na plus stops at Na plus, but Mg2 plus does not. Mg plus does not. Mg is the same, right? Mg is very similar, is 1s2, 2s2, 2p6, and 3s2, 12. Mg plus will give you 3s1. And that's not stable. It has to remove both its electrons to again get to this 2p6 state. And the octet, you might also say, oh, 3s2 is fulfilled. Just leave it like that. The octet, you need 8 electrons, right? Does that make sense? Now, this is about losing electrons. How can you explain Cl minus, F minus, O2 minus?
They gain an electron because the Cl fluorine, they're like right next to the very end, so they have 7. So we just need one more to get to 8.
Yes. It's like more will be given to people who already have, and more will be taken from people who don't have. Just like that. So F minus. So let's start with O. So this is 1s2, 2s2, 2p4, right? So this is 2p4. We're just concerned about this. So 2p4 looks something like this. What do you need to make this more stable? So you need to either remove all these and bring it to 2s2 for a full filled, or you can just take 2 electrons and become a full filled and also get the octet. So you just go from, so you become an O minus first, get 1 electron, and then again get another to become a 2p6. That is why O minus 2 is stable. You don't go to O minus 3, but you go for N, again for the same reason. Cl minus, same reason. You get 1 and become stable. For the same reason, this is called a noble gas. Why? But it doesn't react. Why doesn't it react? It goes, if it takes an electron, if it loses an electron, it becomes unstable. No one wants to do that. Under extreme conditions of temperature and pressure, xenon does it, but xenon is very big. So the shells that are out there are already very energetic. So they might, under extreme conditions of xenon forms, reacts with fluorine. So fluorine is also extremely reactive. So xenon, fluorine, they react. There are various differences. There is XeOF4, XeOF6, all kinds of things that happen. So this is still stable under normal conditions, but push it to extreme limits, there's a break point to everything, right? So does it make sense now? Now let's try iron, because iron is important for Earth scientists and Mars scientists. Iron is very common, so iron is there in the core, so understanding iron is important. It's the same thing. I'm not going to tell you anything new. It's the same thing. So it's 26, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. Did it? So this is 10, 20, 26. Is everyone fine with this? Okay, so now let's go with the last people who got filled in, 4s2 and 3d6. Now, although 4s2 got filled in first because it had low energy, it's outside, a little outside, because it's still 4. So I will draw the D here. Now, you see how 4s2, still being outside, has lower energy? It doesn't, so that's the break point, like between orbit and orbital. It is not as simple. For simple purposes, we can assume that, okay, 4s2 means the 4th shell, and it's like that. But it's a little more complicated than that. But my purpose is not to teach you like quantum chemistry. My purpose is to give you enough idea about these electronic configurations that when time comes about iron chemistry, rare earths and stuff like that, you can actually apply these concepts of electronic configuration to understand their behaviors. Why europium-2? Why you have Fe2 and Fe3? We'll get to know from here. Oh, 3D is 5. Okay, so you have 3D6 and 4s2. So the 4s2 got filled in first, and then you got 3D6. So it fills 1, 2, 3, 4, 5, and then it goes here. Okay, but this is iron. But now, iron, you have seen, so let's assume iron loses an electron. What is the electronic configuration then, when it loses an electron? Where will it take the electron out from? From 3D or 4s? It will take it from 4s. Just when you, so this is the thing. The order might be different. The order, this got filled in first, but this is the outermost because there is a 4. It's outside. Okay? So this will be, the electrons from this will be removed first. Okay? So let's remove electrons. When you do Fe+, so you have all these electrons. Where will it go away from? Or which electron will go? From the D or the S?
The
Sorry?
S.
S. Remove 1. Okay. So you have Fe+. Does Fe+ look happy? No.
Could be up here.
It could be happier. So just remove 1 more. 2. So Fe+ was absolutely not possible because no way iron goes from like this full filled to just +1. It does not. But might do this if there is a electron snatcher available. If there is an electron snatcher available, Fe2+ can become stable. But it can become more stable. How? So if someone is taking electrons, he must best just please take this away too. And let me become this. So it went from partially filled 3D6. So Fe2+ was all this and 3D6, right? So it was Fe2+ was 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, because 2 electrons were off from 4s2. Okay? It went from Fe2+ to Fe3+, and it became 3d5. This is making it more stable because of this. Okay? And that is why this is happening. It will not go for Fe4+, not under normal conditions. Why? It again becomes less stable. Right? Everything is stability. Everything wants to be more stable. Okay? All right. There will be, you can answer most questions in chemistry. So this marks a very important part in the module, because you understood what electronic configuration is. You can, everything, what I try to understand everything through this. Whatever I'm doing, I just come back to this over and over again because it helps you to realize everything is tied to electrons. Like reaction is just electron exchange and between two different entities. Electron exchange, electron sharing, bonding, whatnot, right? So that the things become more stable, right? So these things are, so try and understand everything with this electronic point of view. And let's just, so for your next class, I have this video, I think it's 8. Yes. Please watch this. I wanted to introduce this a little bit. With this electronic configuration, you can exactly understand how the periodic table, the anatomy of the periodic table. It's a 30-minute video. I don't want to do this again here because it's already there. Please watch it. You'll get an insight about the chemistry, about the structure. It's good. So you will appreciate chemistry more. Okay, there is a logic behind it. So chapter number 8 in the same atoms and molecules. playlist, chapter 8, you should do that. Okay, before we go, did anyone figure out this thing? How did you get 35.5? Because if this is true, then the number of neutrons are a fraction, isn't it? What's the number of electrons and protons? 17? You see, I'm not making this up. I mean, it is like in periodic tables, you see a 35.5.
Could it be?
I'm sorry. What they do is sometimes when they get decimals, they take the isotopes and make it like the average mass of all the isotopes and the original one.
Yes, right. Does anyone want to elaborate on that?
I was thinking, because I mean, you see chlorine as a diatom. So.
Chlorine is what do you mean?
Yeah, Cl2. That occurs in nature, right?
That occurs in nature, but
so,
we are just talking about the element here.
So just the element by itself.
Yes, because we are still in that. We are not in the bonding regime yet.
Okay. Well then, yeah. I mean, maybe it could be an average kind of thing. What if there's an electron that has a propensity maybe to like leave the outermost shell, and then in some chlorine atoms it doesn't, and so it's kind of an average of that effect.
It's more simpler than that. In nature, what happens is there are isotopes of everything. Isotopes of hydrogen, oxygen, everything will have an isotope, okay? Some of these isotopes will be, so for hydrogen, I do not remember the exact numbers, but most hydrogens are 1,1. 99.99 or some crazy number is like 1,1. A few 1, 2, and exceedingly rare numbers of 1,3s, which is the tritium, which is used in the radioactivity industry. Which one is used? So this is radioactive and this is heavy water. So this forms the heavy water. So things like that. Exceedingly rare, like very rare, like more than 99% I would believe is 1,1. But just imagine if something like chlorine, I'm making these numbers now, has two isotopes. I think it's 35, 36 or 37? 36?
37.
37, right. So you have these two numbers, but assume that this is not negligible. Maybe this is like 10%. Then when you collect chlorine atoms in nature, 90% of them will be Cl35 and 10% of them will be Cl37. You will have to accommodate both of them. So you will say, what you represent is the average of that. So what you will do is, you will say, okay, the average atomic weight is 90% of 35 plus 10% of 37. Now this will give you the average atomic weight. So whenever you see this, this is an average atomic weight of all the isotopes that are naturally available in nature. Okay, does that make sense? Cool. Yeah, so that's it. Please watch this thing. We are at a good position to understand more and more chemistry. Thank you so much.